Welcome to this session. If you're wondering whether you're in the right place, you are in the right place. My name is Toby Thompson. I work here at Cranfield University. Welcome to this session on decarbonising the oil and gas industry. You'll notice there's a question mark in the title there. This is an IMechE webinar, and we're going to be joined today in the next hour that we're together by a distinguished panel, the first of which, and I want to come to very briefly just to prove to you that this is an interactive session and that we do want your questions on the text chat. We're joined today by Richard Tiplady, who's the chairman of the Oil and Gas Committee in the IMechE. Richard, it's good to see you. Give us a wave there.
Hi Toby, it's great to work with you again on this event.
Brilliant, Richard, thank you. It's good to see you again. Richard and I worked together on one of these events a few years ago. We're also joined by Craig Hodge, who I believe is OTGC, or OGTC in fact, based in Scotland. Craig, is that you there? I've got your name wrong, sorry.
It's fine. Afternoon from Aberdeen.
Aberdeen, good. Thank you. It looks like a snowy background that you've got there. And last but not least, we're joined by Eunice Mullen, who's in Sweden. Eunice, just tell us the name of the town that you are in there.
Yes, hi. I'm in Kista, north of Stockholm in Sweden.
Wow.
In our test site at Climeon headquarters.
It's good to see you, Eunice. And if you want to find out more about where Eunice is, there'll be plenty of opportunity to ask questions. Please keep those questions coming in. They're in the text chat function of Zoom. Hopefully you're familiar enough with Zoom to do that. Type your questions in at pretty much any time during this session, and I'll do my level best to come around to those questions. The last person we're joined with today is Laure Mora, who's based with me in the studio here. Laure, tell us a bit more about yourself and Climeon.
Thank you, Toby. So I am actually a sales manager at Climeon. My background is engineering, electrical engineering, but the role I have in Climeon is what I like to jokingly call a human-machine interface. So basically, I sell the system that we have to clients. A few words about Climeon. Climeon is a technology company in the clean tech industry. It's a company that was founded in 2011 in Stockholm, and the headquarters are still in Stockholm, where actually Eunice will be talking to you from. We have this great piece of technology, which is called a heat power module, full of innovations. And the problem we're tackling here is waste heat. Low temperature waste heat, and how to produce clean, renewable baseload electricity out of this waste heat that we produce as human beings. I can all go and tell you how great Climeon is and how fantastic our technology is, but why would you believe me? I'm a salesperson, so maybe you should listen to someone a little bit more famous than me talking to you about Climeon.
I've been involved with trying to get breakthroughs on clean energy for a number of years now. When I saw what Climeon was doing, I was very excited. You know, we run on energy, and that energy must turn into clean energy as fast as possible, whether it's solar power or whether it's, turning wastewater into energy as Climeon are doing.
If you look at the world, more than 50% of all the energy is dumped as low temperature waste heat. This is a tremendously large energy source that is not used today.
Steel plants, cement plants, aluminium plants.
They are basically throwing away money.
The best way of doing good is if you can actually do it in a way that doesn't cost you a lot of money, hopefully actually saves you money, and does good at the same time. And Climeon can deliver that, and that's what makes it so exciting.
Climeon is a company that has found a way to turn hot water into electricity. This is an entirely new area of clean technology and green electricity. And there is nothing in the world with the same potential. You take the heat, you lead it into the machine, and you make it into electricity. We can also make it very compact. The machine is only 2 by 2 meters.
In the years to come, you're going to get more and more people doing business with companies that are making a real effort to get their own house in order. We will certainly be making noise about it because we're proud of what Climeon are doing for our ships, and we'll let people know.
Our process is so economic that already today it's useful to convert waste heat into electricity.
the consumption of energy will always grow. You cannot stop it because it's a human nature thing.
Wherever there is heat, there should be Climeon box converting that into useful electricity.
Turn this energy into clean electricity and at the same time make a lot of money and save the environment. You can do both.
Gosh, that was quite something. This is a big topic, but what I heard Richard Branson, if I understood the person there talking about, and his colleagues or the colleagues in Climeon, is saving money and the opportunity. So those modules that you saw there, the ORC modules, you have a chance to see later on in this webinar. So if you're already, and I hope you are, intrigued by what Richard Branson is saying around saving money, the opportunity of recovering heat and turning it back into energy, then please type those questions into the text chat box as we go further forward. So Laure, what are you taking from Richard Branson there? Why is he talking about this?
Right, so as Sir Richard Branson said, that the challenges are multiple, and tackling the issue of waste heat is already a big piece of the puzzle coming to help us solve our problems. So as you can see from this video, we have modules installed on board of ships. So not only Virgin Voyage, but we also have different cruise ships and different cargo ships companies using our technology in the world. We also have geothermal power plants, because this is also, low temperature heat. So I'm talking here about low enthalpy wells, so low temperature wells. I'm not talking about the big, flash plants that you maybe have in your mind when you're thinking about geothermal plants. Geothermal come under all kind of shapes and forms. So we've got our technology right now in steel mills, in ships. We're looking at new partnership with gensets application. We've got geothermal power plants. And the reason why I'm here today is we also want and we can help the oil and gas industry to decarbonize. As I just mentioned a bit before, my previous life was in the oil and gas, and I am absolutely passionate about building these bridges between the oil and gas industry and the renewable energy industry. All that to help the whole thing become one big energy industry. They both need each other. So in the UK, when you think about the oil and gas industry, you're mainly thinking about the North Sea. That's where I used to work. I was a drilling engineer offshore in the North Sea.
And I think we have a photograph, of you operating some important piece of equipment, on one of these offshore rigs. But hopefully, Chris, you can see that.
Oh dear.
What are you doing here? What sort of oil and gas operation is this?
Well, this is a very, very sophisticated piece of equipment, Toby. I'm not sure I can describe it. No, I swear I was not just playing golf. I did work sometimes as well. So yeah, this is a very typical shot. I'm sure if some of my colleagues are watching today, they will recognize exactly where that was taken. So yeah, but this place where this picture was taken actually was a production platform. And a lot of hydrocarbons were being produced. And a lot of waste heat was being produced because of the heat at which these hydrocarbons and this water comes out of the ground. The North Sea right now is transforming. It's a necessity. I've just moved back to Aberdeen in the northeast of Scotland, which is the oil and gas capital of Europe. And a lot of people have lost their jobs lately for the reason that we all know. There is a tremendous potential there. The North Sea is transforming and is trying and really having a fantastic journey towards a more carbon neutral future. I think actually we've got someone really qualified to talk about this in the panel, and this is Craig Hodge from the OGTC. Craig, would you be able to tell us a little bit more about that?
Absolutely, yeah. I don't know if I would agree with the really qualified part, but certainly I'll give it a bash, and it's definitely a strong passion of mine. And completely agree with your comments so far. And the reason that we need to transition the North Sea oil and gas industry is because we are still going to need significant quantities of oil and gas, particularly natural gas, as we transition to net zero by 2050. Or 2045, I guess, depending on which side of the border you live on. And This is widely recognised by many, including by the UK government, who released their White Energy paper earlier this week, and the Climate Change Committee, who released their balanced sixth carbon budget last week. However, what we must do with this gas is not only abate the emissions from the end use, but also from how we produce it. And if we can maximise the production from our indigenous resources, in the UKCS, then we can reduce our reliance on imports, meaning that we can control the emissions, as much as possible. Also, over the next 30 years on the road to net zero, we have an incredible opportunity to use the people, the supply chain, and the infrastructure that has been developed around the North Sea's oil and gas industry over the last many decades to create a truly integrated energy system that supports a fair and just transition to net zero. So to do this, we need to decarbonise our oil and gas operations, but we can also use the industry to support the three main areas of growth outlined by the Climate Change Committee, which is renewable electricity, which we can support with the world-leading offshore wind resource in the North Sea. Carbon capture and storage needs to scale up massively, and we've got huge potential with all the depleted oil and gas fields. And we can combine the three of these to produce the large-scale blue and green hydrogen to meet the future energy demand. Now, the organisation I work for, OGTC, our purpose is to support the oil and gas industry to develop and deliver this technology that will enable an affordable net zero North Sea. And this is ultimately why I'm here today, and particularly interested in any kind of oil and gas decarbonisation technologies. So as you said, capturing waste heat, the scale of this is enormous. This will be crucial, and geothermal applications definitely show some potential, but I do think there is more investigation to be done. Both of these ultimately reduce the amount of fuel we burn as we produce oil and gas. And yeah, excited to be part of this panel today and hear more about the technology Climeon have.
I think it's just dawning on me, and I'm not an engineer and I'm not in oil and gas, the size and the scale of what it is that is facing us right now. Laure, can I come back to you? I know you have a presentation that you can talk about, but say more about what it is that Craig was talking about there, that transition. Say more about that.
So I'm very happy you asked this question, Toby, because this transition is something we all need to do, and we all have the capacity to do. We are in a situation of crisis, and not just one crisis. I read not that long ago an interview of both Greta Thunberg and apologies to my Swedish colleagues for butchering her name, sorry about that, and David Attenborough. And they're talking exactly about that, actually. That is not just one crisis. There are multiple crises, and they all originate from one cause, our destroying behavior. But we're also very smart creatures. We all have the solutions in our brains. We have enough engineering power, we got enough idea, we have enough funding in the world to solve it. However, what Craig is describing happening in the North Sea at the moment is extremely interesting, because this shows, once again, there is no silver bullet, and I really want to pass this message across. Do not wait for a silver bullet. We had a silver bullet, that was the oil. A little drop, a lot of energy, you can transport it anywhere, perfect. We cannot carry on using that. We cannot carry on burning the oil because it's damaging our environment and threatening our life. Now, if you're looking for that one silver bullet that's going to replace the oil, it's not coming. The solution lies in a combination of different technologies coming together. And I really encourage you to look at this fantastic report that was written by the OGTC, where you see everything coming together. The hydrogen, the offshore wind turbine, the electricity. Some of them are linked to shore, some of them are too far away. There are all kind of different ways of integrating all that. And that's really what it's all about nowadays, Toby.
Brilliant. I know, Laure, that you've got a presentation to give in terms of what Climeon are doing in this regard. Say more about these modules that we've heard a little bit about, and why Richard Branson is raving about Climeon.
Yes, I can maybe show it to you if we can put the presentation. So just to let you know, I've got few PowerPoint slides. Do not run away, do not leave. I swear I will try not to make them too boring. And especially, Jonas will actually show you the modules that are behind him right now. So it will become more interesting. So as we said before, waste heat is what we try to tackle with these modules. Whether you're talking about low temperature geothermal or waste heat in maritime application or industrial applications, oil and gas application, all this makes sense. So this is the product itself. It's called an HP150. It's a heat power module. That's the current product we have. R&D and Jonas are actually very busy working on the next generation, and they're never stopping, right? There will be one after the other after the other. So they're all based on the same principle. They're called an ORC, an organic Rankine cycle. What is this? It's just a thermodynamic system that derives energy from the difference of potential between two sources. Here, namely, we're talking about hot water, cold water. So you take any hot water or water-based fluid between 80 to 120 degrees Celsius, and a cold source between 0 and 30 degrees Celsius. And you input those two in the machine, and you get up to 150 kilowatt of clean electricity. So this is basically the patented technology we have inside these modules. If you can see here on number 1 and number 4 are two heat exchangers. Number 1 is the hot side, the high pressure side. Number 4 is the cool side and the low pressure side. So your heat source comes in the heat exchanger number 1, transfer its heat to an organic fluid. We call that a working media. It's the fluid that is trapped inside the module. That fluid is being circulated constantly by a pump. So what happens to that fluid? That fluid boils at a lower temperature than water. That's the whole principle of it. So that fluid picks up the heat in the heat exchanger number 1, vaporizes, and goes through a radial turbine. That's what you see at your number 2. That turbine spins and is linked on the same axis on a generator. That generator produces that clean electricity. Now, downward of the turbine, what happened to that working fluid? It needs to be cooled down and condensed to be able to be circulated round and round again. So that's why you have this condenser tank number 3. There, our hot fluid, fresh out of the turbine, meets the cool fluid coming from the cool side, where it's been cooled by your cooling source, number 4. Now, what is your cooling source? Your cooling source could be anything. It could be the sea. On board of ships, that's what we use. We use the sea as the cooling source. You're just thinking North Sea? North Sea, fantastic. Not good for swimming, sure, but great to cool down this type of processes. 6 degrees year-round average, fantastic. So your working fluid gets cooled down in the condenser tank and gets pumped around and around, and it carries on producing your electricity. Now inside, it's not a refrigerant, it's basically an environmentally friendly fluid, and it's off the shelf. So basically that's how it works in a nutshell. Now, why these heat power modules, and why did we make module out of it? It's because we wanted them to be very efficient, flexible, and user-friendly. That's the whole idea behind it. Very efficient, how? So we've got this patented technology that allows us to perform at more than 50% of the Carnot cycle. And for the ones of you who are not familiar with the Carnot cycle, these machines deliver about 10% efficiency in transferring. So basically you get thermal energy in, and you get another energy in the shape of electricity out. 10% of that thermal energy is transferred into electricity. Now, might seem low, but at these temperatures, and for an ORC system, this is the only machine on the market that can reach these efficiencies. It's normally around the 6% mark, and that makes a world of difference. Because if you want this technology to take off, it has to make sense economically. So now if you boost your efficiency up with this patented technology that we have, then suddenly the business cases make sense, suddenly people start using them, and we're doing good for the planet. That's the whole idea about it. Then it's modular. So how modular it is? Basically, you can have that one module functioning on its own, or you can combine it in two different ways. If you have a very hot source, you can cascade this source. It's going to come out a little bit cooler, but it may be still hot to be still used. So then you put another module behind and another module behind, and that's this series arrangement. And what if the flow is really big? You can divide that flow into different branches, and that's the parallel arrangement. And this way, you build up a matrix with these modules, and you build up a power plant that is perfectly adapted to the source you have, making full use of the thermal energy available. So that's the whole idea behind this modular plants. To control the plant, you need an HMI, human-machine interface, and a software. We have an in-house design software called Climeon Live. This software is brilliant because it does everything for you. We've reached a level of automatization that is really amazing. So the idea is also to reduce human intervention on these machines, and that's what you need if we're going to put them offshore in the North Sea, for example. So these power plants can be remotely controlled via this software. The client can look at his power plant, see how much it's producing, see everything is okay. Our service team, so now we have it one in Stockholm, for example, but the idea would have to have, of course, these service teams in Aberdeen or wherever we are needed. They can control the power plants from their remote location. And not just the modules. We also have site controls. So if you have cooling towers, for example, as a source of cold, you have pumps, you have heat exchangers, you have everything that comes around your power plant. This can all be controlled by this software, which is really good. Now, I think it's time, maybe I've bored you enough. Jonas is the head of R&D, so he knows these machines inside out, as well as being an excellent electrical engineer. He's standing in our testing facility in Kista, and he can show you exactly how this works. Over to you, Jonas.
Thank you, Laure, and hi everybody. Great to be here on the webinar. My name is Jonas Molén, and I'm head of R&D at Climeon. And I'm now in our test site in Kista, north of Stockholm. And you can see behind me there is one of those white boxes, the modules Laure spoke about. And I thought I'd start with taking you on a tour of our test site here. And we have prepared a video for you. So if we could please roll that video, I'll guide you through it. So this is where we go in. That's not so exciting, but here is the test site. You see on the left-hand side, a few modules ready for shipment, packed in brown, and then a few white ones, and they are being tested right now. So we test every module prior to shipment. At the end here, we see a strange looking electrical cabinet. And that's test equipment for what we call grid code testing. So it can simulate grid faults. And on the other side of this aisle here, we have large electrical cabinets, and those are power electronic cabinets. On the back side of the module, you see the water connections. So this insulated pipe here has the hot water in it. We can use 70 to 120 degrees C. There's the return. And on the other side, cold water supply, 0 to 35 degrees C, and then the return at the bottom. Nominally 30 liters per second in both the hot and the cold water. And you see that we have several test bays here with the same setup, so we can test multiple modules. On the back here, you have the cables coming out, and the two thick ones are the generator cables, where the power is routed over to the electrical cabinets that change the frequency, basically. This is the HMI, a touchscreen where you control the equipment. One HMI can control using this control cabinet here. Apologize for the installation here, it's R&D style. It contains PLCs and IOs for controlling pumps and cooling towers and what have you. And one of these cabinets and HMIs can control up to 7 units. And like Laura said, they can be connected then in series or in parallel or in different setups to optimize your power output depending on the heat source you have available. So that is a quick guide and introduction to our test site here.
Eunice, thank you very much indeed. There's a ton of questions arriving on the text chat. If you're late to this session, welcome to the session. You have a chance now to ask questions of Eunice talking about those modules. I want to see inside one of those things. But I'm going to go, Eunice, first to a question, a complicated question to you from Emmanuel Pagone, who's asking, does your ORC compare to supercritical CO2 cycles for industrial waste heat recovery?
Difficult to answer in detail, but what I can say is that, what kind of process or cycle you want to use is depending on your temperatures and your heat source. And when this was developed, we targeted low temperature heat sources, cooling water, not steam, and not pressurized water. So we targeted sub 100 degrees zero. And for this range, we have found our setup to be the most optimal. Obviously, if you go to like 200 degrees or another temperature range, there may be other cycles that are more efficient.
Eunice, thank you. Another complicated question. This was from David Jones. Do you feel that systems like Climeon's ORC modules could help with making low enthalpy geothermal projects? Not sure if I got that right. Economic. Can it make those projects economic? E.g. well doublets, by providing electrical and generation, as well as use of water for district heating, perhaps?
Yeah, that's exactly our objective, these low enthalpy sources. So when we started developing this product, we looked at where the biggest volume of waste it is, and that's in low temperature and low enthalpy. And we are exactly trying to do just that. And then obviously it's a case-by-case evaluation. So if you have a very complicated setup with power lines and drilling and so on, the business case can be challenging. If you have a more easily accessible heat source, then it's definitely viable.
Eunice, thank you. I think, Laure, you have a question to add or a point to add to David Jones's question there.
Yes, thank you, Toby. So it's a very good question, and especially the integration that you mentioned with the district heating network. So actually, we're working on a lot of business cases since I've arrived in the UK on the integration of these machines on district heating network in Scotland and in other places. District heating networks are fantastic to reduce fuel poverty and to reduce carbon footprint. The direct use of heat is always the most efficient. However, very often when you look at a CHP plant, or when you, so yeah, you can have district heating network with low enthalpy geothermal, or with waste heat recovery from industrial processes or biomass boilers and all kind of different ways. So for example, we have modules in a steel mill in Sweden that uses the skid cooling water. So basically when you have a piece of steel that comes out of the furnace, it's being cooled down by circuits of water. That water gets extremely hot, and we use that. So basically what happens to this water, it's actually, Scandinavia, you know, is really big on district heating networks. This water is actually warming up the whole town, called Borlänge there. But there is extra heat. And very often in all these systems, there is extra heat. And that's why we have two modules there, to make use of that extra heat and produce electricity on top of that. So yes, we can use low enthalpy geothermal and waste heat recovery for a very good integration into district heating networks.
Laure, thank you very much indeed. And Eunice, if you're still there, I do have another question for you, and there's a ton that's come in here. This one, Eunice, is from David Neal. Can you take the heat source directly from a gas, e.g. a turbine exhaust, or would it have to go through a gas to water heat exchanger first?
That would have to be a gas to water heat exchanger. And that's being done on, not today in gas turbines, but we do that on ship engines. So the exhaust gases go through what they call an economizer and produce steam or hot water, which is routed to our modules. But in the module, we need to have water with the current product.
Okay, and Jonas, a follow-on question from that, from Ioannis. Can you provide some references on marine installations? Has this system been installed in a tanker, for instance, or bulk carriers apart from cruise ships? On a marine installation, what is your main heat source? Is it jacket water, for instance?
So the references we have are, we've been focusing on passenger ships and cruise ships because of the availability of heat and the need for electricity. So that's the kind of, we think that's the sweet spot for us. And we have installations on a ship here in the Baltic, on Viking Line. We've also worked with Richard Branson, as you saw, on his new built cruise ships with Virgin Voyages. The heat source is typically the jacket water, and if you have excess steam, you could use that to boost the temperature a bit, but the main contribution is the jacket water. It's slightly different if you have like 4-stroke engines or 2-stroke, and that's also a reason for us to go for cruise and passenger, because they have a better heat source in their 4-stroke engines.
Jonas, thank you very much. Oh, go on. Carry on, please. Sorry, I cut you off there.
We are also working on a bulk carrier, so that's coming.
Great, thank you. Can I ask one question to Laure, just to follow up on that, and you can go back to maybe some of your slides there. Laure, 30 litres, this is Ben Burke who's asking this question. 30 litres per second is a lot for many older oil and gas wells. How viable is geothermal electrical generation at low flows, as low as 2 to 6 litres per second? I'm not sure if you can answer that one, Laure.
Thank you, Ben, for this question. Yes, so if you look at a lot of wells, so 30 litre per second, let me start with that. The modules start from 10 litre per second upward. So you can start producing electricity with a flow rate of 10 litre per second. 30 litre, so anything between 25 litre per second to 35 litre per second is what we call the sweet spot, as in like this is where you're going to get the most efficiency out of your system. Above that, efficiency will increase, but not as much. And then also at some point it's more economical, or it makes more sense to divide that flow rate and have, for example, 2 modules in parallel. But to come back to your question on flow rate coming out of wells. So yes, a lot of wells do not even reach 10 litre per second, as you rightly pointed out. It's very rare. In my career, I've never seen one isolated well somewhere with nothing around. In general, wells are part of a field. And that's where the answer is, basically. So if you have, if you aggregate the flow from different wells, you don't need to have the flow from the whole field, because keep in mind that the further away you move from the wellheads, the cooler your fluids are going to be. So you need to see exactly where is the best spot, depending on the field, depending on the installation, where to put these modules, where to put your power plant. Do you want a big power plant, 10 modules together after you separate your hydroprocessing facility? Or do you want to aggregate the flow of 2 or 3 wells and have like a mini distributed power plant? Sometimes it makes more sense, and that will depend on a lot of things. That will depend really on what kind of use of the electricity do you have. Do you want to use it on site? Where? How? What's the pipe cost as well? If everything is there already, you might put if all the pipe is there already, you might put everything at the processing facility. If you need to spend money on pipe, you might want to reduce that cost by putting distributed power plants and electric cables instead. And I'm talking here, I have in mind more like land wells in the US, for example, or Canada. Offshore, you have a production facility, you can easily have all the flow aggregated right there, right then. I hope that answers the question, Toby.
Brilliant, thank you. And there's a ton more questions coming in, but please, Laure, you were talking, I think, ultimately about application of this whole thing. So if you can go back possibly to some of the slides that you had there, we'd be keen to find out more.
Yes, actually, and then we see that there are a few questions coming up that are already actually geared towards the oil and gas industry. So basically, this application for the oil and gas industry resides really in two big features. So one of them is waste heat recovery, and you're talking about in an industrial type of waste heat recovery. The other one is geothermal. The oil and gas industry is sitting on this particular spot where they can tackle both of them. They can solve their issue using these two aspects of low temperature waste heat. So how? When we produce hydrocarbons out of our wells. The biggest product of these wells is not hydrocarbon, as you know, it's water, hot water. Billions and billions of gallons of hot water are being produced all the time to bring the hydrocarbons to surface. What do we do with the hot water? Very often it's a problem. You need to cool it down, you need to treat it, you need to reinject it. It costs a lot of money, but it's not being used. That's the main thing. Can we use that? Can we use this hydrocarbon and water mix? Or can we just use the water if it comes after the separator? This is a fantastic source of energy that is being completely disregarded at the moment. This is really a way of looking at the oil and gas, at looking at the first stepping stones into the geothermal world. So that's the idea of using the co-produced fluids, as we call it, to create electricity out of it. So you can do this onshore, you can do this offshore. You're talking about aging assets. So for example, you have an old asset, it's producing more and more water. The water cut increases, and it's becoming really to the point where at some point you're gonna have to have cessation of production, and the dreadful decommissioning date will come. And why is it dreadful? Because it's a cash sink and nobody wants to do that. So can we delay that decommissioning date by starting producing electricity out of it? Right now, on old assets in the North Sea, it's being powered, a production platform, by gas turbines, let's say. You use your own hydrocarbons to fuel these gas turbines. And sometimes you even have to import hydrocarbons to burn these hydrocarbons, to produce hydrocarbons. So is there a way of changing that, basically, of just using the energy you have available right there, right then on the platform? Same on land, like I said, this is an application for both. So if we look at co-produced fluid, that's what we can do. And that's, for me, that's when I think about it, that's the geofluids, that's the geothermal part that we can do. There are also other applications. So if you look at upstream, so same, there was a question, I think, about gas turbines and the exhaust that Jonas answered. So yes, we can use the exhaust heat from these gas turbines. You put an economizer, same as in a ship, and then you boost the temperature of your co-produced fluids and you produce even more electricity. So that's a different way of doing it. Also, if you're looking at downstream and midstream, there are all kind of different applications. Shipping, we have them on cruise ships, we have them on you know, we start also on cargo ships. It's not, we haven't installed one there yet, but it's the same principle. We can do something also for all the shipping aspect of the oil and gas industry. Refinery. I think refinery is also a fantastic place where to start looking at the waste heat. I think, actually, I'm not the best person to talk about that because we have Richard Teplady in the panel. Richard, maybe, is there any insight you can give us on the waste heat in a refinery environment?
Yeah, thanks, Laure. The massive amounts of waste heat in the refinery environment. I have on my desk for our chemical engineering, process engineering colleagues, I've got a data sheet for a fin fan, for a rundown cooler. That's pumping out into the atmosphere 11 megawatts of heat. Now, the opportunity to recover that heat, we're really, really good in the chemical industry and the oil refining industry at integrating high caliber heat, high grade heat. We use it to heat feedstock. We keep the heat inside the process. As soon as we come to low grade heat, which is 200 degrees C and down, we find every way to send it into the atmosphere, whether that be through a water cooling tower, fin fan coolers. And we pump out a ridiculous amount of heat out of oil refineries. Now, I'm really interested to see these solutions. And yeah, we in our industry love things that have been tested elsewhere first. We're not the bravest industry in the world. We like a bit of conservativeness. So a technology that's been tested on ships, tested on geothermal, I think that's a technology we can deploy into our industry. And not just oil and gas. Chemical industry has a high heat, waste heat. The food chain, the food supply industry is a massive heat industry. Sugar beet production or sugar production from beet, massive energy in there. The way you talked earlier about using water as the medium actually mitigates one of my big concerns. One of my great concerns about your units is putting them in the middle of an ATEX Zone 1 area. But with your heat transfer medium being water, it's very, very easy to pump that a small distance to outside of the ATEX zone and deploy these solutions outside of the live operating ATEX hazardous areas. So I'm seeing lots of areas, and I'm sure lots of people on this webinar will be thinking about solutions where they happily throw away heat and they can generate electricity, which is so easy now to recover and send into the grid nowadays, or send into your own consumer-based direct wire energy cells. So really keen to see this solution go forward, and I think we're the industry to take it forward as well. Thank you very much.
Richard, thank you. I got a quick question. It's from Michael. Michael's asking, and I think, Eunice, this might be for you, and it's about electrical ratios. What might be the power ratio, Eunice, between electricity needed to power the modules in comparison to the electricity generated from them? Any idea on that?
Yeah, it depends on how you count it. Inside the module, you have a few pumps and so on. So the net output from a single module is 150 kilowatts to grid, and then it uses 7 kilowatts internally for pumps and stuff. But then obviously on a site, you may have some consumers as well, like cooling towers, circulation pumps, and so on. A geothermal pump will typically be down a borehole or something, so it consumes some power. Those parasitics are very site dependent. It depends on your whole setup, your climate and everything. It could be from 10%, 50% up to 20, 25%. It's very site dependent. So Laure mentioned a steel plant where we have an installation in here in Sweden. There they have Dalälven, a nearby river, as the cold source. So they have, and then they have the existing hot water system on the plant. They have very low parasitics thanks to that setup. Whereas on the other hand, if you're in a warm country and need cooling towers to the atmosphere, they will consume more electricity. So I'd say between 5 and 25% of produced energy, something like that.
Brilliant, Eunice, thank you. And Michael, if you have a comeback to that one, please type it into the text chat. If you've not asked a question so far on this, please do. If you're watching the recording, then you've missed a fantastic opportunity to ask a live question. Back to that electrical point, Laure, I think you're an electrical engineer, so you know a little bit about that. So you mentioned before now about parasitic. Tell us more about that difference between what goes in and what comes out.
Yes, so parasitics is what we call parasitic load, is all the energy, the electricity that is consumed internally. So when we say internally, it could be internally in the module itself, or internally as in the power plant on site. So actually, and that's how we got this efficiency to be so high with this machine, this specific ORC, this HP150, is because we have managed to reduce the parasitics inside the module tremendously compared to the other ORC on the market. And how we did that is not simple. It took 5 years to basically develop and make sure it was working. But basically the idea behind it, just to give you a little bit of the secret, this condenser tank that I showed you earlier on one slide functions under a partial vacuum. And that is a big idea, because that means that the pressures inside the system are very low. That pump that is pumping the working media is working against very low pressures. So suddenly this pump is not using as much electricity as another system would be. And that's how we've been able to basically boost that efficiency, that and also like really efficient heat exchangers. It was quite a challenge technically to fit into these small boxes. But basically all this together is what allows us to be able to have more than 10% efficiency on the conversion from thermal energy into electricity.
Can I come in there? Because I want to, in the 10 minutes that we have remaining on this session, and please type in the question if you haven't already, is some of the bigger issues, some of the wider issues aside from the ORC modules. And one of them is to do with the scale. I want to go back to something that Craig mentioned really early on, with regards to transition and the opportunities. Craig, can you say a little bit more, based on what you've heard so far, about the scale of the opportunity that faces us and the issue that faces us?
Yeah, absolutely, and I'm quite happy to give some more some more numbers for scale, and you know, just to put it into context, the UK continental shelf, our oil and gas production, emitted in 2018 10 megatons of CO2. Now that might not mean a lot to some people listening, but you know, that is equivalent to around a third of what Scotland emitted across all industries. And that is only from burning fuels in gas turbines and diesel engines to produce the energy required to export the gas and to electrically power the platforms. So I think just, you know, that is the scale of the challenge we face, and you know, there's multiple big solutions that can, you know, completely abate these emissions. For example, you know, if you were to power the platform with electricity from a renewable resource, if you could capture all the carbon at the back end of the engine, store it back underground, or if you could switch to a low or a zero carbon fuel, such as hydrogen or ammonia. And there's a lot of research going on in that area, but you know, we've still got, there's still going to be a lot of assets out there producing, burning a lot of fossil fuels that these solutions may not be suitable for. So we need to, you know, basically do everything we can to lower the amount of fossil fuels we're burning, you know, to get down from that 10 megatons of CO2 to zero, you know, to reach net zero as a basin as quickly as possible.
Craig, I know that's not covering your area, but Doug is reminding us that the cement industry is a huge consumer of energy. That you have you installed? Well, this is possibly to Laure, maybe to Eunice. Have we installed energy systems anywhere else? Have you in other big consumers of energy? Richard, you mentioned food. Laure, are you aware of in the cement industry? Is that an opportunity for this sort of recovering?
It is actually. We have looked into it. So we're still. I mean, we've been operating really for only 5 years really since we've got a commercial product, so we're still a very young company. We do not have any installation in the cement industry. We have looked into it. It's a very challenging industry because at the end of the day, the dry heat that comes out needs to be converted into a hot fluid. Now, anything that has really dirty exhaust full of chemicals, it seems trivial, but you actually need a heat exchanger that can take this dirt and this really harsh chemical environment and to transfer that heat into a water loop. And these solutions can be very costly. So that would be really from the cement industry side. If they have that already in place, then yes, then it's a no-brainer. But very often from what we've seen, they do not have these solutions in place yet. And a lot of them are not doing anything with their waste heat because they have to think about the challenge of having a heat exchanger that can take this environment. But definitely this is something we would like to see evolving.
And you have one more slide that you'd like to share with us.
Yes, if that's okay. I'll put it here. And if we could have that next slide on the full screen actually, so everybody can see it quite well. So I was just going to highlight some of the benefits. I think we've talked a lot about it. So you can reduce your carbon emissions. I mean, one of these modules can save 1,000 tons of CO2 per year. It's a lot. So when you put that in the context of what Craig has been saying, for example, that you can see it, how it fits in the puzzle, really. Then, of course, you're reducing your gas turbine fuel cost, maintenance. You can maybe be able to, you know, turn one off and carry on with only 2 of them if you had 3, something like that. You can extend the life of the asset, as I said. But now I would like to really open to something, to like food for thought. So basically, what if you look beyond that? So yes, we're extending the life of an aging asset. What if you don't need to decommission again? What if you can turn this asset into a geothermal power plant? And that's the whole idea. We do not need to decommission this fantastic structure that we have spent so much energy and time doing, and money. We do not need to do all these extremely expensive decommissioning operations that the taxpayer is subsidizing for a big part. we could turn that into a geothermal asset. And for that, we need also a network of an integration into an energy landscape. What are you going to do with the electricity that you're producing offshore? Can you link it to something else nearby? Is it too far from the coast? And I think, Craig, actually, you've got some really good insight on this integration with your role at the OGTC. Would you like maybe to jump in?
Yeah, I can do briefly. Keen, Richard has also got some important things to say about skills transfer, but yeah, certainly that's something we're focused at looking at. In this transition, we need to help the oil and gas industry produce oil and gas with zero carbon emissions, but also utilize the North Sea, the infrastructure, the supply chain, the people to help expand and roll out renewables. And there's huge potential to utilize the supply chain in particular, to become world leaders in offshore floating wind, which is a huge potential for expansion. As you say, if we can, prolong the life of our assets with geothermal, we can then potentially use them for carbon capture and storage in future. And that's just a few of the potential solutions.
Craig, thank you. Richard, I want to come back to you on the skills point. You talked early on about skills, and Laure has just mentioned a much wider ecosystem there. Say briefly in the last few minutes something about the skills opportunity facing us.
Well, the skills opportunity, jumping back to the question about the cement industry. The cement industry has challenges, but the oil and gas industry has a massive skill pool. So we need to join our industries together. The oil and gas industry has predicted that 30,000 jobs will be reducing in the UK oil and gas industry. Well, fortunately, of those 30,000 jobs, they are all highly skilled, experienced engineering professionals who can deliver projects on time. They're going to be the people who can deliver the net zero world to us. For 50 years, they've been delivering the hydrocarbon-led world. And I think in the next 5 to 10 years, those 30,000 skilled people will come across and deliver the net zero world. So take an example, cement plants. Yes, the flue gas is dirty and mucky, but an oil refinery cat cracker flue gas is very nasty. We recover heat from that well, so we can recover heat. We have technologies to recover heat in our industry. We can share with the cement industry. Cement industry is going to be the home of direct air carbon capture. There's a natural joint up between direct air carbon capture and the cement industry, because the output of the direct carbon capture is a feedstock for the cement industry, but it requires green electricity to drive the direct air carbon capture. So if we can have a solution that takes waste heat from the cement industry and produce green electricity, the green electricity can directly run the direct air carbon capture, and that sends a feedstock back into the cement industry. A nice, intelligent, systematic, grown-up link of multiple technologies, but we need the skills, and we have the skills in the UK in our oil and gas industry, and they take no time to transition those skills. You're talking a 1-week training course to move from oil and gas to energy. I think you spend more time relocating yourself than you will do retraining, because the skills are there, and we need to harness those skills.
Richard, thank you. Gosh, there's a lot of work to be done here. There is a question from Callum here, quite a simple sounding question, but I'm not sure, Laure, maybe you can answer this one first of all. And Callum is asking, what pipe materials or insulation are you using to ensure good thermal insulation in the modules? Any idea on that insulation?
In the modules itself?
Well, the pipe insulation.
Oh, the pipe insulation. So I can maybe bounce that back to Jonas if we want to talk about materials. Actually, Jonas, you have any answer on that?
Yeah, sure, no problem. So inside the module, the process is built, or the pressure vessels and piping and so on is built in stainless steel. And then in the heat exchangers, we use different materials depending on what's on the other side. So if you have seawater as a cooling source, you sometimes need titanium plates for that. If you have an aggressive brine in a geothermal case, you may also need something special on the hot side. So heat exchanger plates could be stainless or more expensive depending on the hot and cold source. Otherwise, it's all stainless.
Jonas, thank you very much. And I do have another question. I'm not sure if it's for you or for Laure. And I'm surprised no one has asked this so far, so I'm going to ask it, I'll be the first to ask it, what is the full install cost of a unit? And do Climeon, are you oil and sea offshore trained to maintain that? And how much does that cost? Laura, is that you?
I think that's me. That's the dirty salesperson who's going to answer that. Yes, it's a very good question, because that's really the case of that doesn't make it or break, right? So when you look at the cost of installation, it's widely dependent on the use, on the application. So you're talking from a geothermal power plant where you need to do everything, or you're talking about adding it out to, for example, in a refinery, like Richard was saying, where most of the flow's there, and very often, for example, cooling is already there, so you don't need to add any cost to that. And for that matter, so it depends on what is there already, what needs to be, the balance of plant, basically, what needs to be added to these modules to make the whole thing work. So of course you'll see the most expensive installation where you need to start from scratch, like a geothermal field, and the least expensive ones in a place where you already have everything. So if you take like an offshore platform, you've got already the North Sea, the cooling is going through the platform very often already. The pumping, parasitics already taken care of because you're producing hydrocarbons, so you're not really deducing that. And that brings me also to the fact that your installed cost is going to depend on how many kilowatts you'll be able to produce. And that depends on how hot your source is and how cold your cooling source is. Roughly, I'm going to answer that question. I can see people are like, she's a salesperson, she's not going to tell us.
How much does it cost?
You're counting roughly anything between £3,000 to £4,000 per kilowatt installed. That's how much it costs.
Okay, I thought it would be more, but thank you. Thank you for that, answering that question. We're pretty much out of time, which is a real shame, because there are a ton more questions on the text chat. So I'm sorry if we haven't answered your questions. David Jones had a really brilliant question early on. What are the obstacles? But we can't come back to that. We may have another one of these sessions. You've seen in the scrolling text where to find out more information. So I do recommend you going to the IMechE to find out more of these events. You've seen the information from Climeon today as to where to get in touch with their product. All it leaves me to say now is to thank Eunice in particular for joining us live from Sweden. And thank you, Eunice, for taking your time. Thank you again. Richard, thank you very much indeed. IMechE, thank you for that. And Craig, OGTC, you have an inspiring job there. So Craig, thank you very much indeed. And Laure, thank you for your time and making what I think is a really interesting topic understandable. Even I understand it. Please keep in touch, find out more at the relevant places. Studio production today was by Chris Ripley and David Metcalf. My name is Toby Thompson. Thank you very much indeed for watching.